Okay, so let's do some approximation. Okay, let's do this one first. Approximate sine of 1 over 100. Um, so what do you think you should do? How do you approximate um, values? What did we do last time? So last time we did linear approximation, right? So that was to take tangent lines and then plug in values into the tangent lines. Oh, yeah, for this one, we want to use 2 to the 5th. But let's do sine of 1 over 100 first. We'll do that one later. Yeah, so what's the reference one for sine? So 1 over 100 is close to some value. That's nice for sine. I could probably work with the derivative for. Yeah, it's close. So sine of 1 over 100 is probably going to be close to sine of 0. So look at the tangent line at 0. Okay, so how do you find the tangent line at x equals 0 for sine? What two things do you need for the tangent line? Or just any line in general? Yep, you need a point, and what else do you need? And a slope, good. So what is a point that's near, what is a point that's on the tangent line at x equals 0? Yeah, 0, 0. And what's the slope? How do you find the slope of the tangent line? Yeah, you take the derivative of sine, and then what do you do after that? What do you do with the cosine? Yeah, plug in 0. What's cosine of 0? 1, good. All right, so what is the tangent line? So remember, y minus y1 is equal to m x minus x1, or y is equal to y1 plus mx minus x1. Yes, y minus 0 is equal to 1 times x minus 0. So to simplify that, it's y equals x. Okay, so what is the approximation of sine of 100? Yep, that's it. So L of 1 over 100 should be pretty close to sine of 1 over 100. And L of 1 over 100 is 1 over 100. which is sine of 1. Okay, so that means that small angles near sine are practically the same as the value, which is something we had talked about before. Right? Similar to why sine of x divided by x goes to 1 as x goes to 0. So this is kind of seeing that, for actual values. All right, questions on that? Okay, let's do tangent. How do you approximate tangent of 1 over 100? So we need a point, and we need a slope. What is the point you should probably look at? Yeah, 0, 0. Oh, actually, before we start, can someone plug in sine of 1 over 100 into the calculator? And make sure you're in, actually it wouldn't matter, degrees or radians, because they're both close to 0. Just curious. Oh, that's a lot of, which one was that, degree or radians? Just curious. That was degree. Someone else do radians? I just want to see that. Oh, that looks better, actually. 0, 0, 9, 9, 9, 9, 9 radians. That kind of makes sense, right? A radian is a bit, is it more or less than a degree? Oh yeah, so if pi over 2 is 90 degrees, right? Radians are a lot smaller than degrees in general, right? So 1 over 100 is probably closer to 0 as a radian than it is as a degree. So actually this one's a lot closer. So let's just see it even more vividly. Okay, so let's do tangent. Okay, how do you find the slope of the tangent line? What do you need for the slope of the tangent line of, we're looking at 0, 0? We did it before, so I assume you know it. I'm not saying anything. We need the derivative of tangent, yep. Which is what? What's derivative of tangent? This is one of those memorized ones. Secant squared, yeah. Okay, what happens when you plug in 0? What's secant squared of 0? So remember, whenever you want to find secant or cosecant of a value, just remember what it is. What is it for sine and cosine? Yeah, it's 1 because cosine of 0 is equal to 1. Okay, good. So what is the linearization? So it was the same as sine, right? The derivative for the slope for the tangent line for sine was also 1. And the point was also 0, 0. So that means that tangent of 1 over 100 is very close to 1 over 100 as well. So again, can someone plug in tangent of 1 over 100 in both radians and degrees just to see the difference? Which one was that? Oh, that was degree? Okay. So 0.0001745 And for radians, 0.01000. So again, looks like the radians is a better approximation. So when working with radians, maybe it's better. You get more accurate values in your approximations. All right, cool. All right, so any questions on that? So it was both very close, right? For sine was nearly the same thing because all these repeated nines. And for tangent, it was a little bit above. And for sine, it was a little bit below. Oh, one too many zeros for what, 1 over 100? Oh, okay. Cool. All right, cool. So let's do 2.0001. Oh, how many O's did I do? Zeros? That. 0.001 to the 5th power. Okay, so we're going to do it with linear approximation, and then we'll do it a different way then from the differentials that we talked about last time. And we'll see how we can use the differential. But first let's use linear approximation. So how do you use linear approximation to estimate this? So what is your kind of your base function to work with that you'll need to take the derivative of, etc. X to the 5th, yeah. So y equals x to the 5th is probably the function you want to look at. Where do you want to take the tangent line? Probably x equals 2, because that's an easy one to take the 5th power of. But we'll see that the linearization might be harder because of the 5 there. Okay, so what do we need for the tangent line? We need a point and a slope. What's the point we can use? How do you find the point for the tangent line? Good, yeah, 2 and 32. So this is 2 to the 5th, which, yep, 16 times 2 is 32. That's a 5th power, not 25. Okay, and then how do you find the slope? Yep, so you take the derivative, so f prime is 5x to the 4th, and then what do? With the derivative? Yeah, you plug in 2. Yeah, 2 to the 4th, 16 times 5 is 80. I believe it. Okay. Okay, so what is our linearization? So we take, it's going to be 32, which is the y value, plus the slope, and then x minus the x value. So 32 plus 80x minus 160. Oh, it's an 80x, not 8x. So we have 80x, and then what's that? 128x. Okay, so what do we do with our linearization, our L of x? Not plug in 2, but 2.001, yeah. So L of, and by the way, 2.001, not around, but equal to 2001 over 1,000. So L of 2001 over 1,000 is equal to 80 times 2001, oops, over 1,000 minus 60. All right, so let's do some simplifying. Okay, so we got 4,002 over 21 minus 60. I don't know, maybe want to combine it into one fraction. Four thousand and two minus 1260 over 21. And then what is that? Two seven four two over 21. And that, so when you plug in the calculator, that's around 32.08. Okay, so this is around 32.08, and that's respectable, right? Because 2 to the 5th is 32. So what is actually 2.001 to the 5th? Like the calculator version? How does the calculator do 2.001 to the 5th? Ooh, that's really close. 32.08008. Cool. Okay, cool. So one thing to note is that, I don't know, there was a lot of fractions. Maybe I could have done this easier using decimals, probably. It would have been a lot easier. But we can actually do this a different way. So instead of linearization, we could actually use the differentials to estimate this. So let's do it that way and maybe see if we get the same thing or maybe something different. Let's just see what happens. Wait, sorry. Should it say... Oh, 160. 160, yeah. 128. that changes everything, doesn't it? Okay. This is. Thank you. I was using the 60 from somewhere else. I'm still close though. That was surprising. Okay, what's 128 times 21? Oh, okay. Okay, maybe yeah, let's just use decimals here. It's probably easier. I like fractions too much. 2.001. So 80 times 2.001 minus 128. Yeah, can you do 80 times 2.001? I don't want to do all that multiplication. Probably not too bad. 160.08. Okay, yeah, that's a lot easier. And then, oh, so this one is 32.08. Okay. Cool. Okay. Yeah, thank you. Okay, great. Yeah, thanks. Yeah, so let's use a different method and see if we get the same thing. And we should, based on kind of the theory. So let's remind ourselves what a differential is. Okay, so if this is the curve, and here's the mystery point. X plus delta x. And we know that x was the nice point around it, right? That this was a nice value. So we know when we do the linearization, we get a tangent line, and we have an estimated answer. So what is the estimated answer? It's our L of x plus delta x. Okay, so we had some, so first of all, delta x was our change in x. And there's two corresponding changes in y values. So we called delta x, or delta y rather, the actual change in y. And what we call dy, so what is the change, by the way? It's the change from the y value from x to the y value in x plus delta x. So delta y is precisely equal to f of x plus delta x minus f of x, right? It's this value minus this value. You see that why that's this little gap here? Okay, so that's what we define delta y as. So the actual change in y from one value to another. And that's what this is, right? This is the change in y. So what do we define dy as? This is our estimated change in y. And it's the linearization subtracted by our change. So it's this distance here. So which is precisely f prime of x dx. So this is our estimated change in y. And we figure that out based on the triangle, right? The dy divided by dx. So in this triangle, dx, oh, by the way, dx is equal to delta x. There's no difference there. Dx dy, dy divided by dx is the slope, which is our derivative. And then solving for dy, we get dy is equal to f prime of x dx. Okay, so how can we use this to estimate something like 2.001 to the fifth power? Okay, so based on this terminology, what do you think x is? What do you think x plus delta x is? What do you think delta x is? What do you think some terms are? So remember how we did the linearization and kind of apply it here. So the tangent line is found at x plus delta x. Yeah, so what do you think it is? So let's just start over. How do you find the linearization again? What is the point that you look at for the linearization? Yes, find the nearest approximation. So in our case, what is the closest value that's like nice? Right. So the place where we're drawing our tangent line for us is the closest nice value, which is x equals 2. And the dx, same as delta x, is how much is it off by? So what is this value here? This is 2 plus 0.001 to the fifth power. So for f of x equals x to the fifth, this answer is f of x plus delta x. Exactly that, f of x plus delta x. Do you see that? So just plugging in these values. So this is the x, this is the plus delta x, and this is being plugged into the fifth power function. Okay, so we know that the delta y is equal to f of x plus delta x minus f of x. So solving for, this is the thing we want, right? So let's solve for it, and we get delta y minus f of x is equal to f of x plus delta x. Do we know what delta y is? So remember, I'm using this formula here. Do we know what delta y is? Without a calculator, do you know what delta y is? We don't know. That's the whole problem, right? We don't know how to calculate delta y. Delta y is the actual difference between x, or f of x and f of x plus delta x. If we knew what delta y is, then we'd be done, and we know what our answer is. But what we do know is that the actual change in y is very close to, not dx, dy. Actual, this is the estimated change. Does that make sense? So dy is our estimated change in y. Our delta y is our actual change in y. So if we're trying to approximate, what we want is to approximate this. So we have dy minus f of x is going to be pretty close to f of x plus delta x. Oh, f of fx plus delta x. All right, any questions so far? See just how we're just using the formulas? I get concerned when it gets a little quiet. So I just want to, so if something's confusing, please let me know. So we'll see how this applies in our case. I just want to make sure we see this series of steps here. So this was formula. Here we solved for f of x plus delta x. And then here we approximate delta y. Oh, oops, I subtracted. I meant, yeah, thank you, I meant to add. Yes, so adding f of x on both sides, get delta y plus f of x, so dy plus f of x. Yes, thank you. Okay, so what is dy? We have our formula. dy is precisely f prime of x dx. So f prime dx plus f of x is very close to being equal to the actual value. So this actually looks like the linearization, right? This is like our, yeah, if we look at our linearization, remember our linearization was f of x plus f prime of x, or let's say f of a, f of a, f prime of a times x minus a. This looks very close to that, right? And it's really the same. X minus a is dx. But it turns out calculation might be actually easier when we do this. Okay, so let's apply this to our situation here. Okay, so our x was equal to 2, and our delta x, which is the same as dx, is equal to 0.001. So this is f of x plus delta x. It's going to be approximated equal to, what is the derivative of x to the fifth? . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . 5x to the fourth. So it's close to 5 times 2 to the fourth. What's delta x is 0.001. And what's f of x? It was 2 to the fifth. So this is 5 times 16 times 0.001 plus, that one was 32. 16 times 5, 80. So 80.01, oh, sorry, it's times 0.01. So it's 0.08, right? Is that it's true? And then plus 32. So we have 32.08. So notice the difference between this method and our linearization method. In the linearization, what we did was we were multiplying by 2.001. This was the slope was 80, and then we plugged in the value 2.001. Oh, this is by differentials. So estimating by differentials. So it's not linearization. We get like the same thing. So dy and dx, these are called differentials. Right, so dy, so when we find the differential of y, the differential of y is equal to x to the fifth is dy equals 5x to the fourth dx. Okay, so usually this method is usually nicer when you have decimals, because it's a lot easier to express decimal just by adding it. Right, 2.001 is just 2 plus 0.001. So your delta x expression is a little bit easier to work with. Okay, yeah, so just wanted to introduce that other method. Okay, so any questions on why this is an okay method and how it's different from linearization, but you still get the same thing? Again, you're still solving for right. This is the same value as linearization, because x minus a is dx, f prime is the slope, and f of a is the y value on the tangent line. Okay, so let's continue. So last time, so this was a just nice review for some differential stuff. So let's just do some more differential types of questions. I don't know why I have this page in. Okay, actually, it's probably a good time to take a break. So why don't you look at this question, and we'll talk about what these words mean. Let's meet back at 6:30. But if you remember how we approached a similar question last time, yeah, try it out. And if you have questions in the break, just let me know. All right, it's 6:30, so why don't we continue? Okay, so this question is, we have the edge of a cube that's found to be that is 30 centimeters. And there was possible error in measurement about 0.1 centimeters. So, so we use differentials to estimate the error. Let's first do the volume of the cube. So just a reminder, what's the volume of the cube? No pi for this. So that's you're thinking of the volume of a sphere. That what you wrote is the volume of a sphere. Volume of a cube is just oh, not that big. It's just you take the sides, three sides squared, and cubed, or a cubed, yeah, however you want to do it. Okay, so let's consider the differentials in this problem. So let's say the edge of the cube was found to be 30 centimeters when there's a 0.1 error in measurement. So here's the edge of the cube. So let's say here's 30 centimeters, and there was a possible error in measurement. At worst, it was 0.1 off. From the actual value. Okay, so so if you think of the tangent lines at these extreme points, then or the actual value is somewhere in between here, right? Actual values. What we can do, since we just want to find the maximum error, let's suppose so these are our estimated, or so somewhere in between. So like at worst we're up here or down here. So for differentials, this maybe it was down here. This would be our dy, or sorry, there's a couple dy's, right? So this value here is one of the dy's, and this value here is a dy. Okay, so okay, so let's apply the differential. So how do you find dy? This is our error in our estimation. What is the differential? How do you find the differential? Yeah, so well, just so for dy itself, not doing not doing f plus delta x, but just dy. This is our error in measurement, right? We're computing error. So it's just the f plus delta x, f prime plus delta x times delta x. Okay, so our function here is the volume function s cubed. So our dv, which is we care about, is what's f prime, or what's v prime of s cubed? Just 3s squared, and then ds. So again, this is error in volume measurement. And this is error in side measurement. Okay, so, and this is the measurement. Okay, so what do we measure the side to be? What was our measurement of the side? So it's 3 times 30 squared. And what was our margin of error for the side measurement? 0.1. Okay, so just do that. What is this? 3 times 900 times 0.1. So this is 3 times 90. Which is, it's at 270. And whatever units these are. Centimeters cubed, centimeters cubed. Okay, so this is our, so at worst, we can be 270 centimeters off from the actual volume of the cube. So this is our maximum error. Okay, see how we did that? So ds is our error in the side measurement, and so if we're off by the side measurement, that gives us many different values for volume. So to calculate what that error is in the volume, we can use the derivative, 3s squared, which you can think of as like using the tangent line, and so multiplying by the error in side measurement times the derivative gives us the error in volume measurement, or max error. Okay, so you might think that 270 is is big. So to make the error sound a little bit better for measurement, you can use different types of measure for error. One is relative error. So the max error just means how far off are you possibly from the actual measure. So we can do for relative error is take the you take the estimated measure divided by the actual measure, or divided by. So you take your maximum measure divided by the measure, or error divided by the measure. Okay, so our max error was 270, and the measure that we had of the volume was, so our 30 was the side measure, so our volume measure would be 30 cubed. So it's error divided by value. Okay, so what is that? 27,000. Cool, so that's 1/1000th, right? So that looks very nice. So relative to the volume, and then I think it makes more sense as a percent. You take this and multiply by 100 and get 0.1% error. So relative what the actual volume is, your measurement that's off by max 270 is at most 0.1% off from the actual measurement. So that's not bad, right? 270 might seem really bad, but relatively, that's why it's called relative. If your volume is 27,000 and you're only off at most by 270, that's not bad, right? Does that make sense? Relative, and main one is relative error, and then percent is just turn that into a percent. So it's error divided by value is the relative error. And again, that makes more sense to what's actually going on. 270 as your error might seem a lot, but again, relative to the problem, if you're off by 270 when things are really big, 270 doesn't seem that bad anymore. In this case, just 0.1%. Okay, so let's see how this changes the surface area. That was the other problem. See how this changes the surface area of the cube. So same scenario, but now we're looking at the surface area. Anybody know the surface area of a cube? Yeah, s squared times 6. So if you ever forget this formula, it's very nice to easy to remember. If you can draw a picture. Usually with a lot of surface area formulas, you can use this trick. Like surface area of a cylinder, you can use this trick for. So what is the surface area of a cube? Well, you just take all the sides and add them up. So that's 4 already, right? Then 5, and then 6. And they're all the same. All the areas of the faces are the same. So 6s squared is the surface area. Okay, so let's see how the error affects the surface, our error in measurement affects the surface area. Okay, so what is our, let's call it dA for area. What would our dA be? So this is our error in surface area. Yeah, 12s, right? 12s ds. Yeah, and then you plug in the value. So what was our error? It was 0.1. Error in the side measurement is 0.1. Our measurement was 30. And then 12. Okay, so this is 12 times 3. Was that 36? 36. So our error in the surface area is at most 36 off. So that seems a lot smaller, right? But let's see how it relates to the relative error, right? Just because 270 is bigger than 36, relatively it might be, maybe it's worse for error measurement. How do you do a relative again? You do dA over A. Good. So our dA is 36. And how do you find A? Yeah, you plug it into 6s squared. Yeah, don't plug it into the derivative. That's very important. So plug it into A. So it's 6 times 30 squared. Oh, that looks like it's going to be good. Okay, this divides, so it's 6 over 900. Divide by 3, 300. So 1 over 150. So what's the percent error? So it's 100 divided by 150. 10 over 15 then as a decimal. What's 10 over 15 as a decimal? 0.66. So actually it's worse error. The percent error for our volume was 0.1, but the percent error for our surface area was 0.66. So interesting, right? So you can see that this is 1 over 1,000, and this is 1 over 150. So our assumption that maybe the surface area was a better measurement because it was smaller was wrong. You know, relative to the actual surface area, being 36 centimeters off is worse than being 270 centimeters cubed off for the volume. But still good. 0.66 is nice. Okay, questions on that? Okay. Let's do a tricky one. Okay. So let's say you're painting a dome, and you want to find out how much paint you need. Where the dome is 50 meter diameter, and you want to coat with paint of 0.05 centimeters thick. Okay, I just noticed in my calculation I didn't care about units, so we'll do this together. Okay, so that's one thing we should worry about. Notice that the units are different, so which do you want to use, centimeters or meters? We should probably change it to one or the other. Which would be easier? You tell me. Changing this into meters or centimeters? I think the other way around. I think centimeters would be easier because if you change this to meters, this would be like too many point O's for me to deal with. So maybe change the 50 meters into what is it? Is it 50,000 centimeters? Multiplied by 100, right? So not that. 5,000 centimeters. Or maybe maybe the other way around would be okay too. Or 0.0005. Maybe that would be better. Well, let's see. Let's use when you take the differential. Let's pick one. Okay, so big question is, what am I taking the differential of? So what is going on here? So I have a dome, and I want to paint it 0.05 centimeters thick. So first of all, let's draw it, and then you tell me what formula do you think you'll need. First of all, what is a dome? So they say it's a hemispherical dome. So it's very important to understand the interpretation of what's going on here. So the paint is 0.05 centimeters thick. So there's probably one of two formulas to use, right? Well, let's just do both. Yeah, okay, well, you tell me, what formula do you think you need? It's a hemisphere, so you can give me the sphere formulas, and then we can just divide by 2. Okay, let's think about surface area. So what's the surface area of a sphere? And then we can divide by 2. So it's 1/2 something. So surface area is 4 pi r squared. So the surface area of the hemisphere would be 2 pi r squared. And the other big formula is the volume, right? What do you think the volume of the hemisphere is? Well, what's the volume of the sphere, and then half it? Yeah, so 4/3 pi r squared, pi r cubed. So in this case, it would be 2/3 pi r cubed. Okay, so which one do you think applies to this question better? Surface area or volume? And read it carefully. Any guesses? First of all, why don't we just paint it? Let's say we paint the dome. I don't know, what color do you want to paint the dome with? Let's paint it blue. Okay, so here's painting the dome. Okay. Okay, so the paint is 0.05 centimeters thick, or 0.0005 meters thick. So what am I trying to find? I'm trying to find how much paint I use. So do you think it's volume or surface area? Good, yeah, it's volume. I think it's tempting to think it's surface area, because you're painting it, right? And paint is thin. But the idea is paint has a volume to it, right? You can't, when you paint something, it's not going to just be flat perfectly. It will have some dimension. right? So yes, the answer is volume. So yes, but volume, but you have to subtract the volume of the hemisphere. Good. Okay, so what does this mean is that what is the volume of paint? And I'm going to do this in R and without plugging in values right now. Okay, let's say four. Was it 2/3 pi r cubed? Let's say that's the volume of the sphere without paint, no paint. So you said you have to subtract the volume of the hemisphere. Good. So what do you subtract it by? What is the formula for the paint? Well, not paint, but plus paint. Use dr if you can. Or delta x, maybe. Good, yeah. So plus paint, oops. Right, if this is r, then you're going a little bit extra. So 2/3 pi r plus dr cubed. Okay, so this is what we want. We want to find, this. Okay, so if we read this in terms of differential notation, this is like f of x plus delta x, and this is like f of x. Do you remember what this is equal to? What is f of x plus delta x minus f of x? Do you remember the formula? Yeah, delta y. What is delta y close to? Close to. So this is what it actually is, f of x plus delta x minus f of x. What is it close to? So what was our estimation for delta y? dy, yeah. And then what, so dy is f prime of x dx. So where dx is delta x. Okay, cool. So let's do it. What's f prime? So what's 2/3 pi r cubed prime derivative? Two pi r squared, yes. So 2 pi r squared, and let's use our dr. Okay, so now we have to make a choice, right? Do we want meters or centimeters? So now I'm thinking meters might be better, since we don't have to square 5,000. It isn't square 50. So let's say in centimeters. Oh, sorry, I mean in meters. Okay, so dy is equal to 2 pi. Okay, so what's the radius in meters? That was the diameter. 50 was the diameter, so 25. Sorry, I said 50 squared. Sorry, I meant 25 and then 0.0005. Okay, so what's 25 squared? Can someone do that? Six 25. Okay, and then whatever that is. So that's your answer. Right, so again, this is estimating dy, which is this is dy, which estimates delta y, which is what we determined to be how much paint we need. So, well, can someone do that actually? Plug that in to a calculator? So this y was really v, right? .625 pi. So, oh, which one is? Oh, okay, and it's or 1.9634 meters cubed. So remember, we changed to meters, so this makes a bit more sense. It would be a lot more if it was centimeters. Okay, so that would be the estimation. So maybe you want to buy a, I don't know what that is in gallons, but a 2 meters cubed tub of tank. Okay. 2 5-gallon buckets. Okay, that sounds reasonable. All right. All right. So this is pretty much done with the quiz material. So next time we're going to start with the next chapter, but we're still going to do derivatives. So it's not going to be useless for the quiz. So we're still doing a lot of derivatives. But I mean, let's see. Does anyone have any homework questions, or I could just do like some review questions, or there was a topic that I don't want to start the next section right away. But is there a topic that maybe you're confused about? Maybe want to see an extra problem or two? When is the quiz again? April 6th. So still got a while since we have spring break in between there. Yeah, but next week we're doing new material. So, I mean, if you want to ask me specific questions, now would be the time to do it. Like topic-wise. So the main things we done, 12 for homework 2.4. Main things we did, I think the hardest stuff was probably related rates. Those word problems. Oh, okay, homework 12 for 2.4. But I think doing all those related rates problems help you with other stuff because, 2.4 and you said 12? Because you have to use product rule, chain rule, etc. Implicit differentiation can be tough too. Okay. Here's my 12. The tangent line. Okay, so you have y is equal to x squared minus 1 over x squared plus x plus 1 at 1, 0. So find the tangent line. Is that kind of what your question is like? There'll be a lot of word problems, not a lot. Expect, I would say, 1 related rates and 1 differentials. That would be like a fair guess, because we did a lot of other stuff in this chapter, right? So, and word problems are long, so still be prepared for word problems, but maybe as you do the related rates questions, you'll have more questions about it. Okay, so first of all, we need, oh good, the derivative. Okay, yeah, sure. We can go over some related rates. One of them is really hard. Okay, 2x times x squared plus x over plus 1 minus 2x plus 1 x squared minus 1 over x squared plus x plus 1 squared. And that simplifies. So 2x cubed plus 2x squared plus 2x minus 2x cubed plus 2x minus x squared plus 1. Okay, so cancel, cancel. Okay, that cancels. So what we have left is negative x squared. Well, they combine. We get x squared plus 4x plus 1. So I have something different. Did I make a mistake? 2x cubed plus 2x squared plus 2x, then minus 2x cubed plus 2x minus x squared plus 1. So I have a different derivative than you. Oh, sorry, you have a different problem. Okay. Okay, never mind. Okay, so this is dy dx. Okay, and then you plug in 1, right? This is 1 plus 4 plus 1 over 1 plus 1 plus 1 squared, which is 6 over 3 squared, which is 2/3. You don't need to. No. You don't need to simplify. If there was a separate equation, a separate question of what's a derivative, then you would probably want to simplify, but no, you don't need to. Yeah, so 2/3. Okay, so what is the tangent line? It's y minus 0 is equal to 2/3 x minus 1. So it's y is equal to 2/3 x minus 2/3. So I would check your distribute the negative wrong. That's usually the how it goes. It's some negative somewhere. Okay, someone had a question 1 for 2.4. All right, here's my question 1. Okay, so if f of x is equal to 1 plus 2x squared times x minus x squared. So it's asked to do it via the product rule or via just multiply and then just do the power rule. So this is the product rule. Okay, we'll do that. So dx of 1 plus 2x squared times x minus x squared plus dx of x minus x squared 1 plus 2x squared. Okay, this is 4x, x minus x squared, and then this is 1 minus 2x, 1 plus 2x squared. So we have 4x squared minus 4x cubed plus 1 plus 2x squared minus 2x minus 4x cubed. Okay, so we have negative 8x cubed plus 6x minus 2x plus 1. So now let's see what happens when we multiply. So when you FOIL, you get x minus x squared plus 2x cubed minus 4x to the fourth. So the derivative of all that is 1 minus 2x plus 6x, there's a squared here, right? 6x squared minus, why am I writing things wrong? No, this is 4? No, I wrote this wrong. So 2 and 8x cubed. And these are the same. So that's all it was asking you to do. So first do the product rule, treating it as product, and then multiply and take the derivative by foiling. Sure. Okay, you want to do 2.7, questions 4 and 5. Is 1 the swimming pool one? 7. Yeah, let's do 4 first, because we might have time to do 4. Okay. All right, I'll just use my numbers. You might have different numbers. Okay, I have a baseball diamond. So it's a square, so these are 90 feet. Okay, so this is first, this is second, this is third, this is home. So the batter hits the ball and runs towards first base at a rate of 15 feet per second, 19 feet per second. So the question is, what is the rate of distance to second base? When halfway? Okay, that's the question. So what is the rate of the distance to second base when halfway to first? So I like to, so here's halfway to first at 45 feet. And there are different points in time. Of distance to second base. Yeah? Is that what you have? Okay. Okay, so all right, let's think about this. Are there triangles that get formed every time you do this? Imagine there are triangles involved here, right? What triangle do you think you can make? So maybe I'm giving it away by saying triangle. So you want to come up with a formula for the distance, right? So see those blue lines? You want to come up with a formula to how do you represent the distance at every time? Yeah, right. Good, a right triangle. Now, where is the right angle? So when you draw these right triangles, where's the right angle? It's important, like where you draw the triangle, because then you'll see why it's right. Yeah, at first base. So at every point in time, like you have this triangle, then as you continue, you have this triangle, then you have this triangle, etc. So it's always fixed to be a right triangle when your right angle is at first base. So what is fixed between all of these triangles? What's a fixed value? 90, oh yeah, 90 degrees and yeah, 90, the height of the triangle. This is always going to be 90 degrees, and this is always going to be a right triangle. So we need to find a formula for the hypotenuse, right? So what formula do we have for the hypotenuse of a triangle, of a right triangle? So Pythagorean theorem. So we have c of t squared is equal to a of t squared plus b of t squared. Okay, so when you take the derivative, you have 2c of t dc dt is equal to 2a of t dA dt plus 2b of t dB dt. Okay, so this is c. If this length is a, and this is the fixed length of b, what do we know true about any of these values here in the derivative? So again, we want to find, this is this thing that we want to find. What are some values that we know? Good, yeah. dB dt is 0, since b is constant. So the derivative is 0. What else do we know? Not 90 minus 19. Yeah, 90. But what we can just do is plug in the value at t naught instead of coming with a formula. Sometimes we may not always have a formula. But we do know that dA dt is 19. Or plus or minus. But a of t is, so at t naught, when halfway to first, a of t naught is equal to 45. Okay, yeah, so then we can plug, so first of all, the 2's cancel. So we have c of t dc dt is equal to 45 times negative 19. What's c of t? Or now we've plugged in t naught. That's why there's a t naught here. What's c of t naught? How do you find it? Yes. Well, square root of that. Oh, you mean plus, right? Pythagorean theorem, it's c squared is equal to a squared plus b squared. It's the hypotenuse. So c is equal to square root of, and then it's a squared, which is 45, plus 90 squared, which is the b. So whatever that is. Can someone calculator that? Remember, it's a plus, yeah. Okay. So whatever that is. Well, anyway, so I mean, you can do the rest, right? Now you. I don't have to go all the way to the answer. But that's the setup. So then you find dc dt, which is what our answer is. And there was a second part to the question, right? And it was the same question, but what's going on at third base? Okay, so same setup. But now we're looking for these values. Okay, what's the fixed? What formula can we use to fix? What's a fixed formula we can use that's consistent between all these points in time? Or at least the geometric figure that's fixed? So remember, it's a square, so it's a right angle there. So these are right triangles. So this is the third. So we have these right triangles. This is fixed to be 90. And this is increasing at a rate of, I already forgot, 19. Okay, so same deal. I'm just going to skip right to the derivative because it's the same Pythagorean theorem. C dc dt equals a dA dt plus b dB dt. This is 0 because it's constant. This is 19. This is 45. And, and this, I guess, would be the same thing, right? It would be this is just the same thing, but positive. All right. Yeah, that was it, right? It was yeah, it's the same thing, right? It's a square, kind of expected. Is there a trick question to this, or yeah? Okay, yeah, that's it. So you just fill in the blanks and solve for dc/dt. So one should be positive. So the distance derivative from third is positive because they're getting further away, and the distance derivative to the other one, second, would be negative since you're getting closer. All right, does that help set for that setup? Sure, yeah. Yeah, it's all about the drawing. Um, yeah,